In the musical Hans Christian Andersen, Danny Kaye sings a song that begins, inchworm, measuring the marigold, you and your arithmetic, you'll certainly go far. I'm sure this song is meant as a bit of gentle irony, but I want to take it as a serious challenge. I want to show you how far arithmetic, well, mathematics really, can go towards telling us about marigolds and other living things too. I'm going to concentrate on one of the most important questions in biology. Why do organisms look the way they do? Why do leopards have spots and zebras stripes? Why is it so common for each leaf on a stem to be at an angle of about 137.5 degrees from the one before? How do fruit flies manage to get the right number of body segments and chicks their regular pattern of feathers? Things like that. And when I say I'm going to show you how far we can go with mathematics, I don't mean just using mathematics to help us work out the consequences of models made by physicists and chemists. I mean mathematics in its own right. Actually, most biologists don't even see physics and chemistry, never mind mathematics, as having much to do with this. If you ask a biologist why a zebra has stripes, or a giraffe a long neck, or an elephant a trunk, he'll tell you what those are used for. Zebras have stripes as camouflage, giraffes have long necks to reach the leaves on tall trees, elephants have trunks to pick things up with, and so on. Physics and chemistry are needed to explain how the form comes into being in an individual, but not to explain why this form and not some other. Developmental biology is the study of construction, not architecture and design. One of those who wasn't satisfied with this sort of explanation was Darcy Wentworth Thompson, professor at biology of St. Andrews University throughout most of the first half of this century. His book on growth and form, first published in 1917, is still in print, and it's worth reading if only for the beautiful prose. Let me give you an example. The waves of the sea, the little ripples on the shore, the sweeping curve of the sandy bay between the headlands, the outline of the hills, the shape of the clouds, all these are so many riddles of form, so many problems of morphology, and all of them the physicist can more or less easily read and adequately solve, solving them by reference to their antecedent phenomena and in the material system of mechanical forces to which they belong and to which we interpret them as being due. Nor is it otherwise with the material forms of living things. Cell and tissue, shell and bone, leaf and flower are so many portions of matter, and it is in obedience to the laws of physics that their particles have been moved, molded, and conformed. On growth and form has been something like the King James Version of the Bible. Beautiful poetry and a message that almost everyone ignores most of the time, but if pushed, will admit they ought to take more seriously. One of the few who did try to put Darcy Thompson's ideas into practice was Alan Turing. You may know him for his work on the foundations of mathematics, the early development of the computer, and the breaking of the German naval code during the Second War. Turing was also interested in biology, and about 45 years ago, he set out to solve the problem of Phyllotaxis, the arrangement of leaves on stems. Why that particular problem? Two reasons. First, as biological processes go, it's comparatively simple. The pattern on a mature stem is much the same as the one that was originally formed. Most parts of an organism change their shape a lot more as they grow. And everything happens in the open where you can see it. More than that, however, Phyllotaxis has always had a special attraction for mathematicians. The leaves in a stem are not in general arranged at random, but in one of a small number of patterns. Sometimes each leaf is at an angle of 180 degrees from the one before. Sometimes they occur in opposing pairs, with each pair at right angles to the pair before. But in most flowering plants, and in many others as well, the leaves are arranged on a helix that winds around the stem, with successive leaves at an angle which is usually about 137.5 degrees from the one before. Now, that would be a puzzle anyway, but it happens that 137.5 is the so-called Fibonacci angle. It's a golden section of 360. And Fibonacci also gets into it, because if you number the leaves in the order that they appear along the spiral, then you find that if you start from any leaf, the numbers on the two that are above it and closest to it will be consecutive numbers from the Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, and so on. Which pair they are depends on the pitch of the helix. You can see the spiral in the plant that I just showed you, and you can probably believe that the angle is about 137.5, but a much better example is in the sunflower, where the spirals are much clearer. Naturally, these properties are related. You can derive any of them from the others, but that's another lecture, and it brings in things like continued fractions. But you can see why mathematicians have been attracted to this problem, and why they have tended to believe it must have a simple solution if only they could find it. Kepler, for instance, suggested that because the Fibonacci sequence is generated by the very simple relation that each number is the sum of the two before it, it must be that the location of each leaf is determined by the two before it. This idea is supported by the fact that there are plants in which the nearest neighbors to any chosen leaf have numbers not from the Fibonacci series, but from 1, 3, 4, 7, 11, or 1, 4, 5, 9, 14, which have the same recurrence relation. The angles, by the way, are then 99.5 and 77.9. Despite this, I have to say, Kepler was almost certainly wrong. But while Turing may have been attracted to the problem by its very elegant mathematical nature, he set out to solve it in a very down-to-earth way. He tried to develop a general theory of pattern formation in the hope that the peculiarly simple problem of Phyllotaxis would provide a good test for it. And he based his theory on chemistry, because that seemed the best way forward. It now looks as though his chemical model may not have been right, but it's leading us towards a mathematical one, and I think he would have been very pleased about that. Let me sketch Turing's theory. We suppose that patterns are due to chemical substances which he called morphogens. Turing never said what they were, but there's no shortage of candidates: calcium ions, retinoic acid, things like that. The idea is that if the distribution of the morphogen is not uniform, it can give rise to a pattern. For example, suppose that if it is above a threshold, it will cause melanin to be produced. Melanin is the substance that makes your skin go dark in the sun. The animal will then develop a coat that is partly light and partly dark, with the pattern following the pre-pattern, or template, in the morphogen. Or we can imagine that leaf stems or feathers would form where there are local maxima of morphogen concentration, and so on. But where does the template come from? There's no point in just saying that it was there from the beginning, because if we assume that, we haven't explained anything. We've only pushed the problem back a level. It's like the modern tendency to say that patterns are caused by genes, without explaining how the genes know what to do. What Turing showed was that a combination of chemical reactions and diffusion can produce patterns spontaneously. It's not surprising he should have thought of those two processes, since both reaction and diffusion do occur in living tissue. But it is surprising they can produce patterns, since we usually think of diffusion as smoothing things out. It turns up in equations as a second-order partial derivative. If you have a linear gradient, there's no more diffusion. What Turing saw, however, was that if you had two morphogens, and if they diffused at different rates, then you could get a pattern. Now, here is Turing's model in the way it's generally written down today. We denote the two morphogen concentrations by A and B, and the governing equations are the top two that you can see. Here, dA and d sub b are the diffusion coefficients of the two morphogens. A lot of different reaction schemes have been suggested for F of A and B and G of A and B, and the two I've written down here, the so-called Schnackenberg set, I've chosen simply because they're the simplest. The others all give much the same result, which is actually quite an important point I'll come back to later. Anyway, let's start with this scheme. You'll know that the first thing a mathematician does with something like this is to rescale everything so as to have as few parameters left as possible. The modern fashion is to refer to this as non-dimensionalization, but this is such a spectacularly ugly word that I prefer not to use it. Anyway, we make the substitutions that you can see, and the result of it is that we end up with these equations, which are rather simple. You'll notice there are only two parameters left now: beta, which is the ratio of the diffusion coefficients, and gamma. Gamma represents more than one thing. As you can see, the square root of gamma is proportional to the linear size of the region. Gamma itself also represents the ratio of the reaction rates to the diffusion, and so you can increase gamma in a number of ways. Now, we can solve the equations by a computer, and in a moment I'll give you some examples of what happens when we do. But we can actually get a better understanding of how the process goes without a computer. Computers are wonderful things, but they often deliver numbers rather than an understanding. Besides, Turing, who had more or less invented the computer, didn't have a PC on his desk, so we can follow through a little bit of what he had to do. Remember, we're trying to show you how you get a pattern out of nothing. So let's suppose that we have static homogeneous concentrations of both U and V, the scaled morphogen concentrations. That means that both the time derivatives and the space derivatives must be 0, and that gives us equations for the equilibrium concentrations U sub 0 and V sub 0. It's easy enough to solve these, and therefore we find that we actually do have a solution. That is to say, there is a homogeneous steady state. But the word stable, which I slipped in when I didn't mean it, is actually the clue to the whole problem. Because if the state isn't stable, you won't observe it. The way we find out is by asking what would happen if we moved very slightly away from the equilibrium. So we let U equal U sub 0 plus little u, and V be V sub 0 plus little v, where both U and V are small. And we then substitute in and we drop all terms that are of higher order than linear and U and V. You'll notice, by the way, that the first term in the equation has disappeared because that was set equal to 0 in order to find U naught and V naught in the first place. When we carry out a similar calculation on V, we find that U and V, that's little u and little v, satisfy these two equations here. Now, we can actually get the solutions of this fairly easily. I could just point out that if the partial derivatives with respect to x weren't there, we would have something like exponential growth, so we expect an exponential in t. If that derivative wasn't there, we'd have something like simple harmonic motion, so we'd expect sines and cosines in x. So you can imagine that the solution should be of this form, and in fact they are. Unfortunately, there's a lot of them, so the complete solution is like this, and that's an infinite sum, which fortunately doesn't matter because we don't actually want to know what it is. All we want to know is whether the equilibrium is stable. Now, if all of the lambdas are negative, it doesn't matter what these terms are, because of course if you wait long enough, they'll all go to 0. So U and V will tend to 0, and since these are the deviations from equilibrium, it means the system will go back to equilibrium, that is, it will be stable. And we can easily show that there are lots of parameter values for which this happens, so the system can have a stable steady state. It turns out, however, that if you alter the parameter gamma, for example by making the region longer, letting the thing grow if it's an embryo, this will change the values of the lambdas. And providing that beta is not too small, one of the lambdas will eventually go positive. The corresponding term in the summation will therefore grow rapidly. So now, instead of having infinite series with all the terms 0, you'll end up with infinite series with all but one of the terms 0. The other one will grow, and so what you're going to have is a cosine function with a steadily increasing amplitude. This doesn't mean to say that in the end you end up with an infinite amplitude, because of course as soon as the term u or v gets large, the approximation we did in the first place is no longer valid. But it does give you an indication of what happens. And in fact, when you integrate the full equations, you discover that it's not a bad approximation at all. The wavelength depends on the parameters of the system, and how many peaks we get depends on the wavelength and the length of the interval. It's a lot like standing waves, except that it comes about in a quite different way. Depending upon how we think the model works, this particular example could represent 3 dark regions and 4 light ones, because you can see these correspond to where we're above the threshold level. Or alternatively, it could represent finding the locations of leaf primordia or segmental boundaries or something like that. These correspond to the maxima of the concentrations. I've done all this in 1 dimension. Much the same thing happens in 2 dimensions, at least for the linear case. But you find that when you do the full integration in the 2-dimensional case, you do not get a checkerboard pattern as you might have thought. The modes in different directions interfere with each other, and you get a pattern which is on the whole rather messy. though it does have the property that the number of changes of color in any direction is approximately equal to the length in that direction. Now, mathematicians generally like to work with rectangles and circles because they're simple, but on the whole, they're not really very interesting. And so about 15 years ago, Jim Murray, who was then at Oxford but is now at Seattle, decided to see what would happen if he did something more realistic. So he integrated the equations over domains that were chosen to look like animal coats. And now let's look at a few of his results. What he found was this. He integrated over these shapes for different values of gamma. Now remember, one of the interpretations of gamma is that it represents the size. So while these have all been drawn as the same size in order to get them in the graphic, you have to think of this one as being very small and this one as being very large. The idea is that if you have an animal which is very small, then it probably won't have a pattern because there just isn't room for any of the pattern elements to appear. As the animal gets bigger, you pick up first of all one mode in the longitudinal direction, then you start picking up a two-dimensional pattern, and as I said, these tend to be not regular. The pattern then becomes spots because you've got more changes of color, until finally the animal gets very large and now the pattern variations are too small and they disappear. And this explains why it is that on the whole, rather small animals tend to be unpatterned, rather large animals tend to be unpatterned. I'm thinking of mice and elephants, and in between you do see patterns. Now, you may be thinking that first one is a little bit unreasonable, surely, but in fact, there are animals that look like that, and here is one of them. There are a couple of puzzles about this, you might think. What about the giraffe? Giraffes are large, but they do have patterns. I brought along one just to show you, to remind you, and also to indicate that a proposed explanation of this is in fact the embryo of the giraffe is very small at the time when the pattern is laid down, and that's what matters. I have to say, however, that I have heard biologists argue about this one, so we only have to take it as a possible hypothesis. However, there is one case that really works rather nicely because we can prove a theorem, and this theorem it pretends to be true. And the theorem is this. It is that spotted animals can have striped tails, but striped animals cannot have spotted tails. The reason for this is very easy to see. It's because if there isn't room across the body for a transverse pattern, then there certainly isn't room across the tail. And in fact, if you look at animals, you find that on the whole, there are lots of spotted animals with striped tails, but there are none that I know of that go the other way around. The interaction of the modes in a two-dimensional pattern implies, among other things, that the pattern will be very, very sensitive to the details in the shape of the boundary, to irregularities in the skin and things like that. And this means that on the whole, individuals from one species will tend to be similar in that if one has splotches instead of dots, others will have splotches instead of dots, but the details of the patterns will be quite different. And this is quite true. If you look at a herd of Frisian cattle, for example, you will see that while they all have the same basic pattern of large black and white patches, you never find two that are exactly identical. Notice that the reason for this is not that it gives any particular advantage to the animal, though I've heard people claim that perhaps it does, but rather it's just the way that the physics and the chemistry work. Let me mention just a little bit of my own work. Many organisms are segmented. Now, a Turing mechanism can easily produce segments, we've seen that, but there is a problem, because how many there are normally depends upon the length. And in many animals, the number of segments is exactly fixed. It has to be, because otherwise the animal is badly designed. We find also that the length of an embryo can vary by as much as, say, 20% at the time that the segments form. And yet, if you're going to have 16 segments, which is what a fruit fly has, you'd have to be correct to within about plus or minus 3%. And that was assuming all the other parameters were right, which of course they're not going to be. Now, I thought about this for a while, and then I had an idea. Suppose you wanted to cut a loaf of French bread into 16. How would you do it? Well, obviously, you'd cut it into half, then you'd cut each piece into half, and so on. Nature, I decided, must do the same. And of course, there was other evidence from experiments in the laboratory I was working with that this was the case. And we were able to show theoretically that this was really what one would expect to happen. You might say, yes, that's fine for Drosophila because 16 is a power of 2, but what happens if the number is 15 or 23 or something like that? And that's fairly easy too, because you only have to suppose that one of the divisions fails. That does not, as you might think, leave you with segments of different sizes, as it would in the case of bread, because in biology, the patterns are usually laid down first and the size is adjusted afterward. If you like, topology comes ahead of geometry. Those of you who know the Danny Kaye song will know that over the original song, there is a bit of counterpoint that goes 2 and 2 R4, 4 and 4 R8, 8 and 8 R16, 16 and 16 are 32. Well, you see, surprisingly enough, what the inchworm was saying was relevant. Of course, it wasn't relevant to the marigold. He was talking about himself, but if Danny Kaye didn't know that, I suppose we shouldn't be too surprised. Having got this far, I ought to let you in on a secret. The Turing model is very clever, and it's very simple. But there's no evidence that it's how pattern formation always occurs. In fact, there's no real evidence that it's how pattern formation in organisms ever occurs. And it's only recently, 5 years ago or thereabouts, that it was ever observed in the laboratory. So you might think I would find this discouraging. In fact, I think it makes the whole idea more interesting, but I'd better explain why. You see, reaction diffusion is not the only method of pattern formation. There are many others that have been suggested, and doubtless more that we haven't thought of yet. They tend to be more complicated than reaction diffusion, at least mathematically, and so people tend to use the reaction diffusion model as, if you like, a model itself. And it turns out there are a lot of similarities between the reaction diffusion model and all the others. One of them is that, other things being equal, the number of elements in the pattern does depend on the length. So a lot of what I've said still applies. In particular, it's still hard to get 16 segments in one fell swoop, and a lot easier to get it by successively splitting the thing into 2. So the result seems to hold that whatever the model is, reliable pattern formation still has to occur sequentially, a bit at a time, not all at once. And so we can say that in biology, almost any reasonable mechanism for pattern formation will have that property. But why will it have that property? Is it because of physics? Is it because of chemistry? No. It's because of mathematics. It seems to be a mathematical property which is common to all of the models we can think of. And so we can say that if reliable pattern formation in biology has to occur sequentially, that is a mathematical result. It's a direct mathematical contribution to the subject. We've already seen an example of this in the Turing model because it works for a whole lot of chemical reaction schemes. So even there, we saw that the details were unimportant. It seems, therefore, there are some mathematical relationships and patterns that are important in nature. That may remind you of what you may have heard about the Middle Ages, because then people thought things like the heavenly bodies must go round the earth in circles because circles are perfect. If they're perfect and special mathematically, they must be special in nature as well. Well, we seem to be getting something like it today. The difference, of course, is that now we have much better reasons for identifying certain mathematical structures as being important in nature as well as in mathematics. And for example, if you've seen catastrophe theory, you will have heard of René Thom's 7 elementary catastrophes. These are one example of the sort of structures we can look for. And one of the most exciting tasks, I think, of applied mathematics in the future is to look for more of them. That may have sounded like a closing line, but I'm not quite finished yet, because I want to go back to Phyllotaxis. Turing never did solve the problem. He began work on a paper called Outline of the Development of the Daisy, but his tragic death occurred before he could finish it. Other people have tried to use his ideas to model Phyllotaxis, but without a great deal of success. Then about 5 years ago, 2 French scientists, Douadet and Coudet, carried out an absolutely fascinating experiment. They set up a pair of electric coils in a Helmholtz array with a vertical axis. Below them, they placed a flat plate coated with silicon. It had a very small hump in the middle and a circular disc at the edge. They allowed drops of a magnetizable fluid to pass through the coil, thus becoming magnetized, and fall on the plate. When they hit the plate, the hump moved them slightly off spot, and then the magnetic field pushed them towards the ditch. When only one drop at a time was on the plate, then of course the direction in which it moved off was random. But when a second drop was allowed to fall when the first one was still there, it was repelled not only by the magnetic field, but also by the first one, and so set off in the other direction. If a third reached the plate while two were still on it, it was affected by both of them. But since this one was further away than this, the influence of this was stronger, and so it set it off at an angle something like this. As the rate of drops became faster, then each drop was affected by all of the ones before it that were still on the plate, and the angle changed. But as the speed of the drops increased, the angle between each drop and the one before it tended to a limit. And the limit was, well, of course, 137.5 degrees. What else would it be? Duati and Coude were also able to show why this happens, physics being simpler than biology. They realized that because they were dealing with magnetic droplets, and these are dipoles, there was an inverse fourth power law, and not an inverse square law. They wrote down the equations, solved them on a computer, and they showed, of course, that if you allowed the drops to come fast enough, the angle would be 137.5 degrees. So this was fine, except it left the puzzle as to what all this has to do with phyllotaxis. I mean, surely we're not trying to claim that what happens in plants is that the leaves are magnetized and they repel each other, and that's where the angle comes from. Or maybe you think that it is that, or maybe you think that, well, perhaps it's some other mechanism which has the same equations. Perhaps it is. But Duati and Coude found something even more interesting. They did their calculations over again, only this time they said, well, instead of assuming an inverse fourth power law, why don't we assume an inverse square law, standard sort of thing? And they got the same answer. Or maybe we should suppose that the force between the two is exponential, and they still got the same answer. It seems that all sorts of different mechanisms with all sorts of different relations and all sorts of different equations all give you the same angle, 137.5 degrees. There just seems to be a deep mathematical reason, one that we don't yet understand, which is producing that angle, both in the magnetized droplets and in the flowers. Obviously, we'd like to know what the actual mechanism is for the flowers, because we don't yet. But in order to understand why the angle is 137.5, we don't need to know that. It seems it's mathematics that can tell us why. Let me suggest just 2 points you might want to think about. First, how does this affect your view of whether mathematics is a science? We've all been taught, at least for the past 150 years or so, that mathematics is not a science because it's not about the real world, it's about patterns. After all this, are you so sure? The other point is, people often wonder what mathematicians do for a living. Well, this is the sort of problem that mathematicians like to solve. What is the mathematical property that means that a whole range of different mechanisms all give you the same answer? What is the whole class of mechanisms that will do it? Does this class divide into subclasses with slightly different properties? I don't know, but I'd like to, and I hope somebody finds out. Finally, let me remind you of the end of the song. Inchworm, inchworm, measuring the marigold. Seems to me you'd stop and see how beautiful they are. Some people claim that if we study something with our heads, we can't appreciate it with our hearts. I don't see why. I mean, if understanding something was a barrier towards appreciating it, then it would be a bad thing to teach children musical instruments. Though I have to admit that sometimes scientists, we do get so caught up in problems that we forget why it is we wanted to know. If you like, we get so interested in finding answers that we forget what the question was. Turing never forgot. I thought you might like to see this drawing that I found in the archive at King's College, Cambridge. It shows the 10-year-old Turing looking at daisies when he was supposed to be playing hockey with his friends. And a friend of mine who knew him well says that throughout his life, Turing never ceased to wonder at the sheer beauty of organisms, and in particular daisies. And I suppose that's not really surprising, because if you talk to more conventional biologists, a lot of the best of them will say that the reason they went into the subject in the first place was because it's about beautiful things. But for mathematicians, there's another side to it. We too find our subject beautiful, even though many people say they can't understand that. There is something about the patterns that arise, the way things fit together, the elegance of the arguments, that we feel no word but beauty can describe. I find it very satisfying to think that there is a link between the beauty that we can see in our subject and the beauty that everyone can see in nature. There's no need to tell the inchworm to stop and see how beautiful things are. That's precisely what he's doing.